Well, hello everyone. It's so nice to see you. Ha, ha, ha. Yeah. So if you're in my Wednesday classes, I'm not here today. So I figured this was the best way for us to stay on track was for me to create a little video lesson for you. So we're going to go through the PowerPoint that you will find online, posted on It's Learning, and then there is an assignment that you'll be able to complete in ClassKick. Please notice that we have some homework here on page 205, numbers 5 through 8, 11 to 13, and I'll check all of this homework next Monday. Next Monday, we will review in class. We'll do some practice, or for those of you who are in my Thursday class, on Tuesday, we'll do some practice problems. And then on our next class, which is a week from today, we'll be taking our test on this functions unit. So today what we're going to be looking at are inverses, and students will use properties of inverses and the horizontal line test in order to determine if the inverse of a function is in fact a function. So hopefully you took that time to copy that down and you were able to get that working. I also hope that you are able to read my writing and typing, as I did not bring my XP pen home with me to make this video. So I'm hoping that you'll be able to read what I've written. And if not, we'll fix it all later because that's what we do. Okay? So moving onward and upward. Okay, so when we find the inverse, now finding an inverse of a function isn't necessarily something that's new. And if you read the textbook definition, by the way, this is section 3.8 in your textbook, finding the inverse of a function says to recall that a function can be considered a set of ordered pairs in which the first element is paired with exactly one element of the second, with exactly one second element. If you switch the coordinates in the pairs, the resulting set of ordered pairs is called the inverse. So basically, there's the key. When you switch the coordinates in the pairs, the resulting set of ordered pairs is called the inverse. So this actually comes about when we switch our x and y. So to find an inverse, you switch x and y coordinates. Now, if you're looking at a graph, that means you're going to reflect over the line y equals x. So if you're doing it graphically, you're actually reflecting over the line y equals x. And we'll look at that also. But that's how you get what the function is going to look like, if in fact the inverse is a function. Because it is possible that the inverse of a function is not a function. And we'll look at some like that as well. But you need to be able to recognize how to get a function. So first things first, let's take a look at this set of ordered pairs, and it says to describe the inverse of a function. Well, remember, when we're describing the inverse of a function, we want to switch. Switch. Don't take no mess from nobody. Switch. Okay? So that means you're going to change your x's and y's. So instead of this first ordered pair being the ordered pair -3, -5, the new inverse is going to be -5, 3. And that 3 is negative. We didn't change the signs. We just changed the order. Then our second ordered pair would be 0, -2. Then our third ordered pair would be 3, -1. Then our fourth ordered pair would be 4, 0. So all I'm doing is taking each single ordered pair and rewriting it so the y is the x coordinate. So then we have the ordered pair 3, 1. And then we have the ordered pair 0, 2. And then we have the ordered pair -5, 3. So that's my set of ordered pairs. So what I'm going to do is I'm going to put that in the set notation because that's how you're supposed to write a function that is in the set of ordered pairs. Now to describe the inverse, what we basically do is we just take the same letter we had for the function and we put it to the -1 power, it looks like. So this is the notation right here for f inverse. Okay, so that's how we write the inverse of f is written as f to the negative 1. Even though it doesn't mean the negative 1 power, it just means that we have the inverse. Now, so we've described the inverse here. So our next step is to say, is this a function? Well, in order for it to be a function, each first element has to be paired with exactly one second element. So I have negative 5 is negative, oh, nope. Negative 5 is used twice as an x-coordinate. 0 is used twice as an x-coordinate. 3 is used twice as an x-coordinate. So is this a function? No, our inverse is not a function. Our inverse is a relation. So f inverse is not a function. Now, if I lost you, go back and rewatch that. Go back and take a look at it again, or ask somebody beside you. Because all we do to find the inverse is we switch our x and y. Now, same thing happens here. It says to give an equation for the inverse described by y equals negative x squared plus 4. All right, so I'm going to do an inverse here. All right, so I'm just going to call this y inverse. And that's going to be when I switch my x and y. So I now have x equals negative y squared plus 4. So I start by dividing both sides, or excuse me, subtracting both sides by 4. And I have negative y squared. Then I could divide both sides by negative 1. So I would have negative x plus 4 equals y squared. And then I'm going to take the square root of that. So when I take the square root of that, I have the square root of negative x plus 4 equals, because when you take the square root, you get the absolute value. So that means that y is actually plus or minus the square root of negative x plus 4. And if you feel better, you could write it, because I don't really like seeing that negative in there, plus or minus 4 minus x. And that's going to be what our graph looks like. Okay, so what we're going to do is we're going to just pause for a second. And so take a second, follow the algebra. That's what this is. This isn't trig. This part is algebra. All right, we just solved that inequality, solved that equation. Now it says to sketch a graph and the inverse on the same set of axes. So just like always, I'm going to go to Desmos. And I'm going to sketch y equals negative x squared plus 4. Make sure that was my equation. Yes. And then I'm going to also sketch y equals, actually I think I could do, yeah, I'm going to do y equals, and I'm going to see, do we have a plus or minus sign here? I do not see a plus or minus sign. So I'm going to do the positive square root of 4 minus x. And I'm going to do the negative square root of 4 minus x. Make them both the same color so it looks like it's all one piece. Now you could have also done that with the absolute value of y equals the square root of 4 minus x. So you could have sketched it that way. Now, when we said this, we have both functions on our graph. We have f as our original and we have our inverse. They're sketched there. Now, just to be sure, y equals x, there's my line y equals x, and you can see it intersects in two places. And when I look at my table of values for there, and I look at my table of values for here, I guess I have to do it like this. Okay, I can compare. So at -2 we have 0, then at 0 we have 2. At 0 we had 4, so at 4 we have 0. So you can see they just switched over those axes. Right? And you can see that this ordered pair right here is 1, 3. So that would mean the 3, 1 would be on here. So if I look at 3, 1, it's not marked. Oh, because I don't have, if I turn my table off, I'd be able to see it. But I can see that that's 3, 1. I also have 4, 0, and the inverse. And then on the original, I had 0, 4. Here I had the ordered pair 0, 2 on the inverse. I had 2, 0 on the function. I had -2, 0 on the inverse. I have 0, -2 on the function. So all we did was switch our x's and y's. So if we go back to our PowerPoint, there's what our graph looks like. Now, when we do that graph, is the inverse a function? So, well, if the inverse is a function, that means that the inverse passes the vertical line test. So if you took a vertical line and slid it across here, would it pass the vertical line test? So just hold your pencil up, take it across, looking at the green graph. Does it pass the vertical line test? And the answer is no. It does not pass the vertical line test. So this is another case where our inverse is not a function. Now, we could have predicted that because this is symmetric to the y-axis, so that means that each x has only one y, this y has two x's. So when we flip it over the y equals x line, each x is going to have two y's. So just a little tidbit there. So there's how we do the algebra part of this. So that's what we're looking for. We just switch our x and y, and boom. So here's another one for us to try. So it says to first consider the function f of x equals 1 divided by x minus 3, and then plus 4. Give an equation for the inverse. So to find the inverse, we're going to switch our x and y. And remember, f of x is the same as y. So we really have y equals. So this is really x equals 1 divided by y. Yes, you're right, I almost wrote an x, plus 3, minus 3, plus 4. So then I want to solve this, so I'm going to subtract 4 from both sides. Equals 1 divided by y minus 3. So I want to solve this for y, so what I could do, treat it like a proportion, cross multiply, so I have 1 equals x minus 4 times y minus 3, which means now I've got to divide by x minus 4. And that equals y minus 3. So this time we would add 3 to both sides. And that would equal our inverse. So that's our inverse function. Then it says to graph f and its inverse on the same set of axes. So if I go back to my Desmos, I can do that. So I had y equals 1 divided by x minus 3 plus 4. So I can see that that's a translation that I went right 3 and up 4 from my parent function of 1 over x, and then my new function I forgot what it was, minus 4 and plus 3. Okay, and when we look at that, if we were also to graph y equals x, so we can see that these points right here are the ones where they're the same. So if I look at this ordered pair here, this ordered pair is 3.16 and 1024. So if I come down here to 1024, I've got 3.16. Yeah? So there might be some easier ones we could check. So like here we have 3660. So on this one we should have 0, 366. Here we have 0275. So on this one we have 2750. So you can see some key points, 10 and 3167. Oops. And 10. So you can get some nice points to compare, and you can see that these are inverses. Now, is the inverse a function? Well, if I graph x equals a number, if I graph a horizontal line here, or excuse me, a vertical line, or if I look at my graph and I took a vertical line across it, does the inverse, which is the blue one, pass the vertical line test? And the answer is it does. It just has different asymptotes. So our asymptotes switched also. Notice up here our asymptotes were x equals 0, excuse me, x equals 3, and y equals 4. Now they are x equals 4 and y equals 3, because remember what we did. We switched our x's and our y's. So what used to be a horizontal asymptote at y equals 4 now has the horizontal asymptote at x equals 4. Excuse me, the vertical asymptote at x equals 4. So those reversed. So let's try another one. So now it's asking you to find an inverse for the equation. Find an equation for the inverse of f, and then is the inverse a function? Support your answer, and then sketch the inverse of both of those. So to find our inverse, we switch our x and y's. So we have x equals 2 times y minus 1 squared plus 3. So we're going to subtract 3. Then we're going to divide by 2. Then we're going to take the square root. Right? So that means that this is plus or minus the square root of x minus 3 divided by 2 equals y minus 1. And so then we could add 1 to both sides. And that's our F inverse. Now that had a little bit more algebra to it, so take a second and see what you got. Oops. Is the inverse a function? I'm going to say no, because this was a parabola. So all I have to do to show that it's not a function is find one point that's going to repeat. So if I put in, let's see, 4. 4 minus 3 is 1. 1 divided by 2 is 1/2. So I have 1 plus 1/2, which is 3/2, and 1 minus 1/2, which is 1/2. So I put in x and I got positive 3/2 and positive 1/2. Two different values for 1x. So my answer is that this is not a function. It is not an inverse. And so when I'm supporting my answer, what I want to do is I want to show that I have 1 point or 2 points that make it not an inverse. So for it to be an inverse, each x has to have only one y. So if I substitute that in, so let x equal 1. So when x equals 1, oh excuse me, I said 4, didn't I? So I would have 1 plus the square root of 4 minus 3 divided by 2, which is 1 plus or minus the square root of 1/2. So I do it once with plus, so I have 1 plus the square root of 1/2. And then I do it once with 1 minus the square root of 1/2. And I realize now when I was talking through that, I forgot that I was doing the square roots. So let me just go to Desmos again. And I'm just going to do my scientific calculator. I'm going to do 1 plus the square root of 1/2. And then I'm going to do 1 minus the square root of 1/2. And those are two different y values for the same x. So since that x has two y values, it's not a function. So this was 1.7 and this was 0.3. So we'd have the ordered pair 1/2. I'm sorry, we'd have the ordered pair 4 and 1.7. And we would have the ordered pair 4 and 0.3. And then to sketch this on our Desmos, we can go up here and we have y equals 2 parentheses x minus 1 to the second. And I think there was something else there, wasn't there? 1 to the second plus 3. Okay. And then if we're just going to graph it, we could just switch it. X equals 2 parentheses y minus 1 parentheses squared plus 3. And there are our two inverses. And you can see this isn't a function because it fails the vertical line test. Now we knew it wasn't going to be a function because here when we do the horizontal line test, it hits 2 points at a time. Isn't that the same as doing the vertical line test to the inverse? Yeah, it is, because it's reflected over the line y equals x. All right, so the next thing says, given any two functions f and g are inverses if and only if f of g of x equals x for all x in the domain, and g of f of x equals x for all x in the domain. What does that mean? That means like what we did on Monday and Tuesday where we did the compositions, we put one function into another function. That's what we're going to do here. So if we substitute the g function into f and it equals x, great news. Then we have to do the opposite way because we know that composition, the order matters. Okay, it's not a commutative property one. So then we substitute f into g, and if it equals x, then they are inverse functions. Please be aware of this function. Okay, so let's try one. So first off, we're going to look at these two functions. What is the domain of f of x? When I look at the domain of f of x, it's all real numbers except 0, right? Then if I look at the range of f of x, it's all real numbers except -5. Then if I look at the domain of g, it's all real numbers except -5. And our range is all real numbers except 0. So I'm liking what I'm seeing here as far as these being possible inverses. So what I want to do is I want to find an equation for f of g of x, and I want to find an equation for g of f of x. So you see what I'm saying here? I'm seeing that the range of f is the same as the domain of g, which means that everything that comes out of my f function can go into my g function. So what I want to do is I want to check that out. So we're going to find an equation for that. So we're going to take the g function and put it into the f function. This is going to look ugly, but it is what it is. So we're going to have 2 divided by 2 divided by x plus 5 minus 5. So that is our f of g of x. All right, so right here, I see this is division. It's fractions division, right? So that tells me I really have 2 times the reciprocal. So when I do my algebra there, the 2's cancel out. And I have x plus 5 minus 5, which when I simplify that, that equals x. Dudes, what does that mean? Nothing. It means nothing. It means that it is possible that f and g are inverses. It doesn't guarantee that they're inverses, but it means it's possible that they could be inverses. In order for them to be inverses, g of x has to go in to our function. So what would our domain and range be for this? Well, our domain is the domain of f, or excuse me, the domain of g, which also works in here, the range of g that works in here. Well, so our range of g was all real numbers except 0, right? That works here because we can't let this be 0. So our domain would be all real numbers, but x does not equal 0. And what's our range? Our range would be all real numbers, but y does not equal -5. Okay, you probably noticed this. I made a mistake here. I stated the domain for the wrong function. So if we're plugging in G, we want to look at what the domain of G was. And our domain of G was all real numbers except -5. So that's our domain for f of g of x. We still can't be -5 because if we put -5 in there, it's undefined. Okay? Boom. That's it. We're not going to worry about what the range is. So let's take a look at the second half, because now that we know that this f of g of x equals x, now we have to test the second part to see if in fact these functions are inverses. So let's take a look here. So now we want to find our g of f of x, which means we're going to take our f function and plug it into our g function. So we're going to take this and put it in here. So we've got g of f of x equals 2 divided by 2 divided by x minus 5. That replaced our x plus 5. So that means we have 2 divided by x minus 5 plus 5, because there was nothing to do to those parentheses. So now we can combine like terms, and we have 2 divided by x, which means that's really multiplying. So that's 2 times x divided by 2, which gives me x. Which means since f of g of x equals x and g of f of x equals x, they both are inverses of each other. So this is a situation where these two functions are inverses. If you are asked to show that they are inverses, these are the steps that you go through. Now, what's our domain of g of f of x? Well, our domain of g of f of x is the domain of f of x, because that's the one we substituted in. So our domain is going to be all real numbers, but x cannot equal 0, because that was the domain of f. Is that right? Now, this is going to be available on It's Learning. This will be on YouTube for you to go back and view. You can check it out. I'm going to ask you to work on the practice that's on ClassKick for the rest of the period. Okay? If you can't get on ClassKick for whatever reason, you can work on the homework that's been assigned to you, but you'll still need to do the ClassKick assignment. Okay? Hey, thanks for coming out today. I look forward to seeing you guys again in the near future. Bye-bye now.